Hi, in this video I will show you the video experiment results of the paper, SoNIC, Safe Social Navigation with Adaptive Conformal Inference and Constrained Reinforcement Learning. This work is done by the Trustworthy Autonomous Systems Laboratory of UC Riverside. First, let me show you the simulation experiments. In the in-distribution tests, which means that the test results are generated in the same distribution as the training setting, we find that the SoNIC model can generate yielding behavior that makes little intrusions into human trajectories, and this behavior pattern enables SoNIC to achieve very high success rate compared with previous state-of-the-art reinforcement learning methods. For example, in this scenario, the robot using previous state-of-the-art reinforcement learning models chooses to approach its goal directly at the very beginning of the episode. This leads to an almost inevitable collision since the robot gets stuck in the crowds. In contrast, SoNIC moves out of crowds to avoid intruding on other humans' trajectories, thereby preventing the risk of getting stuck. We also notice that SoNIC exhibits good emergency responsiveness and can handle the conditions where nearby humans have sudden changes in their moving directions. In this scenario where there are humans having larger velocities than the training settings, we can see that the prediction model is incapable of correctly predicting the future positions of these humans. However, the ACI-generated prediction uncertainty can quickly adapt to this condition and regulate the behavior of SoNIC to generate proper decisions in this OOD scenario. In this scenario, the behavior policy of surrounding humans is changed to the social force model, and we can see that SoNIC adapts well to this change and successfully navigates to its goal. Next, I will show the experiments conducted on a real robot, which is equipped with 4 mecanum wheels. Let me first show you the visualizations of prediction uncertainty on the real robot system. We observe that the human walks around the robot, and their position is correctly detected. At first, the prediction lines for longer horizons exhibit greater uncertainties compared to those for shorter horizons. Then the human stands still behind the robot, and the areas for prediction uncertainty shrink quickly after a few steps of iterations. Next, I will show the yielding behavior of the real robot system. In this scenario, we can see that the robot will stop, yield, and move from behind the person. Next, I will show the behaviors of the robot in sparse crowds. From the video, we can see that the decision ability of the robot equipped with SoNIC model is quite stable, even when the humans have very random moving patterns like running towards the robot. The full clip shows that the robot can generate stable and repeatable yielding behaviors when interacting with crowds. Next, I will show a full trajectory of the robot moving through crowds in the goal-reaching navigation mode. In this video, the goal of the robot is shown as the orange circle. We can see that the robot moves towards its goal in a conservative and courteous manner to avoid collisions and intrusions into the prediction uncertainty buffers of other humans. Next, I will show 2 long-range navigation scenarios where the robot can navigate much longer distances compared to the training phase. We adopt a moving goal located 5 meters ahead of the robot along its longitudinal direction, while maintaining the same lateral position as the robot's starting point. This moving goal guides the robot to move forward over a distance significantly longer than what it encountered during the training phase. This is the second case of long-range navigation. Here, we place a static agent at the position of the pillar on the terrace to represent static obstacles. The robot successfully navigates around it to avoid a collision. Afterward, it continues moving forward and successfully navigates over a long distance. That's all. Thanks for watching.